Are we doing it?
Yes, sir.
Yay! Hey everyone, watching this. Could be 100 years into the future. That's the power of video.
Wow.
Isn't that crazy? You might be watching this on Mars.
I'm watching on Mars.
Everybody in here laughing. They might be watching on Mars. All right. It's a little off the subject. So, if the particles can move through the membrane, then they might spread out. That's called diffusion. Diffusion is the normal spreading out. And we would say that there's a concentration gradient. You all know what concentration gradient means?
Mm-hmm.
What's the concentration gradient? That's the normal movement of particles. And in this case, what is going on? In this picture, the concentration gradient would be going that way for the particles. The concentration gradient is the normal way that the particles usually spread out. So if I had a bunch of things on this side, and not very many on this side, which way would the concentration gradient for those particles be going?
Right.
From left to right? From right to left?
Left to right.
From left to right. And it's usually shown with arrows like this. That's the concentration gradient. The way the arrows are going. But cells, what cells tend to do, Charlie, are you with me?
I'm looking at the syllabus.
What cells tend to do is to pull particles against their concentration gradient. The molecules normally want to go that way, but cells want to actually concentrate particles inside of them. Why would a cell want to concentrate particles inside of itself? To use them. What if it needed food? It's got food inside of it, but it wants more food, doesn't it? So it can pull food in from its environment and pull these molecules in. But that takes energy. Anytime you're going against the concentration gradient, it takes energy. So what does a cell do? It uses transport proteins. Now, a transport protein is a protein in a membrane like this one. This one that you see here is just a channel protein, where stuff can go through. You can see there's a high amount of potassium on the right side of the picture. Potassium is the purple square. There's a low amount of potassium on the left side of the picture. So potassium is going to naturally move from high concentration on the right to low concentration on the left. The potassium will spread out. That's what diffusion means, it's just spreading out. So there is a concentration gradient going from right to left, and the potassium will move through it. But concentration gradients aren't the only gradients inside cells, or that control movement in cells. There's also what we call electrical gradients. Electrical gradients have to do with charges of ions. Notice on this side of the picture are a bunch of sodium ions. See all the sodium ions?
Mm-hmm.
There's also some good amount of chlorine ions. Chlorine ions are negative, sodium ions are positive. The positive charges repel other positive charges. Do y'all know that like charges repel one another?
Mm-hmm.
So cells also have to worry about that. Now, if there's a whole bunch of positively charged particles on the left side, the potassium's not going to want to go in that fast. Uh-oh, phone's ringing. Should I answer?
No.
Tom, Willis. Okay. Thanks. Charlie, will you pop out the side door? Your mom needs to give you something.
Right now?
Yep. Mr. Willis is back. Jack. So if there's a whole bunch of sodium ions on the left side, the chlorine's not going to come through as fast because it's repelled by the sodium. If you put more chlorine ions over here on the left, they'll stick to the sodium ions. And it'll make less positive charge on the left, and the potassium will come through faster. Let me ask you a question. See if you're so smart. Are y'all paying attention here?
Yeah.
Don't yell out the answer. Think about it, and then I'll call on someone. In the old days, like they used to do to embarrass kids. Worked very well, actually. So, what if I added a bunch of OH minus ions on the left side? What would that do to the diffusion rate of potassium? Thomas,
Make it quicker.
if I added OH minus ions on the left side? Is he right?
What do they stick to the
Or just make it bigger and then make it slower.
If we added OH minus ions on the left side, they would stick to the sodiums, which are positively charged. That would mean there's not as much positive charge on the left side that's free, and the potassium would go through faster. You're right. They doubted you.
You know,
You proved them wrong. Let me ask this question. Don't shout it out. If you added a bunch of hydroxide OH minus ions on the left side, what would that do to the pH on the left side? Don't shout it out. What would that do to the pH on the left side? Oh, why are you shouting it out?
Stupid.
Let me call on somebody. Dylan, what would it do to the pH on the left side?
It would decrease it.
Is he right? Would it decrease the pH?
I'm gonna say yes. No.
It
I'm
would
gonna say,
make
I'm gonna say both.
Yes. it would.
You got to understand what pH is.
I'm just gonna say no. You're rebel.
pH is a scale from basically 0 to 14. A low pH is what?
acidic.
An acid. A high pH is what?
A base.
A base. If you're very acidic, what ion do you have a lot of?
H+.
H plus. If you're very basic, what ion do you have a lot of?
OH-.
OH minus. If there's the same amount of H plus and OH minus, what's your pH?
7.
7 is right in the middle. Because water is H plus and OH minus. Do we understand pH yet?
Yes.
Matt, are you listening to this? This is good stuff. So, if you add a lot of OH minus on the left side, they'll bind to the sodium, the potassiums will go across faster, and what will the pH be like on the left side?
More basic.
It'll be more basic, so it'll be higher or lower.
Higher.
So was Dylan right?
No.
Yeah.
These are tough questions, aren't they?
Mhm.
Are y'all thinking here? Can we get these? Who we got over there? Oh,
My computer.
Ellie left her computer. Oh, you need your computer. Nothing.
Okay. Thank you.
Meryl, you don't have a computer?
No, I have an extra.
Where's your computer?
It's dead in my locker.
It's dead in your locker?
Do you want mine? Very good.
I have a sharding cord you could have borrowed from me. Even better, charge your computer next time. So we have concentration gradients and we have electrical gradients we got to worry about in the cell. Are you worried about either of them? You should be. There are 3 different kinds of transport proteins in the cell. Uniporter proteins just transport the thing through. That's what this looks like it can do. It can come right through all by itself. That's a uniporter protein. Symporter proteins usually have the thing they want to transport comes through, but it can only come through attached to something else. We call that a symporter protein. So for instance, like if sodium was going to come through, it might be able to only come in through if it's attached to a chlorine. You know what sodium and chlorine together are called?
Salt.
Salt, sodium chloride. Salt is just kind of a general term. It stands for a positive and negative ion attached to one another. But yes, it is a salt. Are y'all liking this chemistry stuff?
Oh, yeah.
The coolest ones, I think, are antiporters. The molecule needed can only come in if a different molecule is transported out. Those are called antiporters. Have you ever heard of the sodium-potassium pump?
Yes.
It brings sodium in while pumping, it brings potassium in and pumps sodium out of a cell at the same time. The sodium-potassium pump. This is actually showing how the sodium-potassium pump works. Here's a sodium ion in large amounts. This up top is outside the cell. Down at the bottom is inside the cell. What happens is sodium will stick to this transport protein. And by the way, you're very likely to be asked about the sodium-potassium pump. For some reason, the textbooks just love it. And it's used a lot in cells to move stuff. So sodium comes in here, it attaches to this protein. ATP is necessary. Remember I said it takes energy to pull it against this concentration gradient? That energy comes in a molecule called ATP. On my magnets, this is ATP. There's a DP and there's P, and they come together to make ATP. And the ATP will come up to a protein. Let's pretend this is a protein. The ATP will come up to the protein and drop off its P. And then the protein will change shape in some way. It often goes from that to that. From that to that. And so it might be like this. In this case, with the sodium-potassium pump, the sodium ions come in and attach to the protein. The ATP drops off its phosphate, and the protein basically opens up on the other side and lets the sodium go across. So it'd be like we had some sodium. Let's pretend these are sodiums. It'd be like if sodium came through here. Watch this. It attaches right there, and then the ATP comes in. Click. And whoop, this changes shape like that. And then the ATP comes apart, and now we have ADP. The P will stay attached. We say that the protein has been phosphorylated. Can you say phosphorylated?
Phosphorylated.
That means we added a phosphate to it. And then the sodiums can come out. And then maybe a couple potassiums will come in. Let's say these red ones are potassiums. And then the phosphate will break off, and then it'll go back to the shape it was before and let the potassiums in. Isn't that cool? That's the sodium-potassium pump, baby. It's pumping away. It's churning away right now in every one of your nerves. Your nerve cells just sit there. They're right now. They're pumping sodium out, potassium in, and maintaining that difference. We call it a potential difference, and so it stays charged on the inside of your on the outside. It makes the outside of your nerve cells carry a positive charge. The inside carries a slightly negative charge. And then you can just fire a nerve cell when it's time. Somebody touches your finger, pew! It fires an electrical impulse. And you feel it, oh, this is touching my finger. You look over at some dude and you're like, oh, weirdo touching your finger. All that happens real fast. Would you like to see video footage of the sodium potassium pump?
Yes, sir.
Video footage of the sodium potassium pump. Let's YouTube this bad boy. Very common video. Sodium potassium pump. Here we go.
Why not the amoeba scissors?
Amoeba scissors too annoying.
Oh.
Active transport is a type of cell transport that requires the input of energy in the form of ATP. The proteins that conduct this form of transport are often called pumps because they force molecules or ions to move from an area of low concentration to an area of high concentration. This is commonly referred to as against the concentration gradient. One of the more common examples of active transport is the sodium-potassium pump. The job of the sodium-potassium pump is to move sodium ions, or Na+, out of the cell, and potassium ions, or K+, into the cell. Let's take a closer look at how this happens. The sodium-potassium pump has binding sites with 3 sodium and 2 potassium ions. Let's follow the movement of the sodium ions first. After 3 sodium ions are positioned within the carrier protein, an ATP molecule is split, releasing phosphate. This phosphate binds to a location on the exterior of the carrier protein, causing the protein to change shape. As the protein changes shape, the 3 sodium ions are released to the other side of the membrane. Next, 2 potassium ions position themselves within the carrier protein, causing it to undergo another change in shape. In the process, the phosphate molecule is released. Once the phosphate molecule is released, the carrier protein expels the potassium ions into the interior of the cell. The carrier then resumes its initial shape, completing the cycle. Notice that for every 3 sodium ions leaving the cell, 2 potassium ions enter. Since both sodium and potassium ions have a positive charge, this unequal movement causes an electrical gradient to develop across the plasma membrane of the cell. A number of cellular processes, including the generation of nerve impulses, use this electrical gradient.
See, if you pump 3 positives out, but only 2 positives in, it's going to be more positive on one side than the other. And that charge, that electrical difference, is what we call our electrical gradient. It's actually called an electrical chemical gradient because it uses ions to carry the electric charge. And so it's nice to have kind of a charged area on the outside that can help move things along.
Heck yeah.
Charged area on the outside and charged area on the inside. Now
it's crazy.
this is called cotransport. So here we have a molecule like glucose that we want to bring into the cell. Glucose will attach to this protein, And this protein's like a spinner. When glucose attaches, I don't know why they have the glucose as a rectangle here, and they have sodium as a hexagon. I would have put glucose as a hexagon if I was writing it. But you know, what do I know? Just some dude, right? I'm just kidding if you're watching this. I know you're good. You're good at your job. That's what I like about you. Alright, anyway. The glucose attaches. The sodiums also attach. And the whole thing spins around and then drops off the glucose and the sodiums on the other side. So that's an example of co-transport where both of them can cross at once. Picture's actually a little screwed up also here. This thing spins around, then that should put the glucose on the right side and the sodium's on the left. Am I correct about that? So they screwed that up too. Sorry, dude. You're 0 for 2. But it does look like, it kind of looks like that thing Batman throws. So for that, I salute you, sir. Or ma'am, might be. So anyway, both of these are getting pushed against their concentration gradient. No, I'm sorry. The glucose is getting pushed against its concentration gradient. The potassium is moving down its concentration gradient. So, normally molecules like to move down their concentration gradient. So the glucose, the sodiums will just come right through without using energy. And their movement, their energy of movement this way is probably enough to pull in the glucose against its concentration gradient. So that's a good cheap way, without using ATP, of pulling through the glucose. Make it use the energy of motion from these sodiums going with their concentration gradient to pull in the glucose. Isn't that clever? Clever cells. Is this also this section?
I don't think so.
Can we move to another section?
Nope.
Got any video footage?
Hold on. Okay, that's it. Can you stop filming?
Yes, sir.